I'll just briefly recap what we covered, and there were also some things due to some questions which I'll sort of say here today, and yeah, then we'll move on from there. So basically the things that we covered were the following. So yesterday we were mostly talking about phase transitions. And so we covered the following. First we saw that near continuous phase transitions, using the fact that there are fluctuations at all length scales, we could convince ourselves that that immediately means that appropriate response functions diverge. And we sort of gave two examples here. We could look at specific heat, for example, and that was related to the fluctuation of the total energy. Which one? Oh yeah, of course, sorry. Otherwise it's identically zero. Yes, yeah, I have also eaten a lot of food. Yeah. Right. Okay, so the fluctuation of the energy is basically related to specific heat, and therefore for a continuous phase transition, this is expected to show a singular behavior near the critical temperature. And then let's say for the kinds of things we have been hearing about, let's say the 2D Ising model or the 3D Ising model, we also saw that the magnetic susceptibility, in particular the zero field magnetic susceptibility, is also related to the fluctuation of the magnetization, and in the Ising problem, the 2D ferromagnetic Ising problem, and even in the 3D one, the total magnetization acts like an order parameter. So the fluctuations of the order parameter are again related to this response function, and it diverges. Okay, so that was the first thing we saw. So actually, let me point out a simple thing from here, which is the following, so which I just didn't explicitly say last time. So suppose you're slightly above Tc, right? So you're coming from a high temperature, and let's say you're slightly above Tc, and then I can just say that expectation of m is 0. Then let's say I just look at this part, m squared. Now you see, what is m? M is just summation Si, right? So then what is m square? M square is just square of that. So this guy is just related to the correlation function. This guy is just related to the correlation function, and basically this thing is like beta times v times, if you wish, S0. Let me fix a particular site, SR. Sorry. Let's say it's a d-dimensional system, DDR, right? Something like this, right? Just from this relation. So there is a relation, there is a very nice relation between the correlation function that you have been hearing about and the susceptibility, right? Now, you see, in general, we have been discussing that this correlation function has a behavior like this, right? So it's an exponentially decaying behavior. However, you can easily see that if you get something like this, and then you try to do this integral, you would get something finite, right? Because the only way this integral can diverge is due to its large R behavior, and at large R, this integrand itself is small, right? But then, to get a large response function here, this thing should break down, and the only way this thing can break down is that this diverges near a continuous phase transition as we approach Tc, right? So I didn't explicitly point that out, so I just did that here now, and it's clear from this relation.
So at Tc, there is 1 by r to the power d minus 2 plus eta.
Correct, correct.
So this is like anyways not there, e to the minus r by z.
Oh, that's correct, but as PK was also saying, there's also a power law sticking here. Correct, correct. Right. But the point is, this length scale has to smoothly go to infinity, Otherwise, this response function cannot diverge. Okay, so good. So that is another thing. Then then one more thing that we discussed, which is quite important, is that there is an effective ergodicity breaking below TC, right? What that means is, we in fact even saw a Monte Carlo demonstration of that, of course for small system sizes. What that means is, if one is below TC and one starts the system in, let's say, a state which is predominantly composed of up spins, then the system takes a long time to then go to a state with predominantly down spins, even if the system is finite. And we in fact estimated that long time, right? We in fact estimated that long time, and that time basically scaled, oh, there's a big mosquito. Oh, yep, now it's gone. Basically scaled as something like that, divided by KBT. Okay? So of course you can see that this time scale diverges very fast, and of course this is the fundamental reason. So we saw that for these Ising type systems, and this is the fundamental reason that we see phase transition even for finite systems, right? Okay, good. So that was another thing. Then one thing which I'll today slightly improve upon is the following. We gave this domain wall argument. We saw what was the entropy cost to generating domain walls, and then we realized that they actually proliferate. So we gave that argument for the d equal to 1 Ising model, right? And today I'll just slightly better that argument, because I realized that we can even get an estimate of the correlation length from that argument. So I'll actually just point that out now. So yesterday I didn't realize it. Okay, so let me continue with this d equal to 1 Ising model, and we'll soon see, we'll basically just discuss yesterday's argument, and we'll see what's going on. So suppose I create one domain wall. This is one domain wall, right, as we discussed yesterday. So basically it's a king, and then spins on this side are all, let's say, one sign, spins on this side are all another sign. Now you can easily imagine, and creating one domain wall effectively costs you something like a 2J of energy or something like that. Now you can create two domain walls, right? That's not a problem at all. Something like this, and that has an energy cost of 2 times 2, 4J, right? Now we have to ask our question, ask ourselves the question that what is the degeneracy of such kind of a state, what is the degeneracy of such kind of state, and so on. So of course the only thing I need to say here is that how many walls do I need, right? I just need to specify two locations on my lattice, and the first wall comes here and the second wall comes here, right? And so suppose if I want m walls, then I just need to specify m points and I can move them around, right? So then that's a combinatoric problem, and that's basically C n choose m, right? That's the entropy of this. And then we can take the logarithm of that, and then we'll see something nice soon, okay? So the energy cost of m domain walls is 2 times m times j, right? We just count the number of domain walls, and the counting for how many possibilities are there is exactly the number of choices to choose those m points on the lattice, right? Because then after we choose the points, we just lay the walls there, and that's it. Good. So then let's just use that, and I'll also use this Stirling's approximation here, because I'll assume that there's a large number of walls here, but you already know this, right? So I'll just give you the simplified thing. So basically, as I said, the free energy gain that you get is, so now we are considering m domain walls. So this number here is, m here is 2, but m can be anything that I want, and you'll soon see why am I doing this, okay? Right, something like this. So then I use Oh yeah, there is a slight overestimation, but for a big system we can ignore that. Right, that is true. There is a slight overestimation, but yeah, this is reasonable. Yeah, because most of the time, yeah, especially if you have dilute, yeah, right, good. So I'll also use this, right, the Stirling's approximation, because I'm assuming that both n and m are large, and furthermore, I'll define a density of these domain walls like this. Okay, good. So then I use this simplification here, and I'll just proceed with the result. Okay, so the result is, after you just use this simplification, you don't need to use anything else, is delta f. So of course now delta f is a function of x, right, this ratio, because everything else is determined there. Okay. Good. So this is delta f, the free energy gain for a density x of these domain walls, right? Now the question is, how would I determine this x, right? I have been given some free energy, right? And then, yeah, that's correct. How do you think I would determine x? Somebody said the right thing. Right, because that's the only unknown parameter here, so I can just differentiate with respect to x. And put that answer to 0, right? And actually that will determine x. That's the important thing, right? So it will basically determine the density of the domain walls. Okay, good. So once you do all that, I'll just write down the results, because you can do this thing yourself. So yeah, I'll just write down the result. So what you actually get is that x is the following. Okay, so this is the density of the domain walls. So what does it mean? So suppose then I ask you, what is the average distance between two domains? How can I estimate it from this number? No, so this is the density of the domain walls, right? Now I ask, what is the average distance between the domain walls, right? So if the density is very small, the average distance is going to be, of course, large, right? So it's just an inverse relationship. Okay, good. So I just take the inverse of that. That's like the typical distance between two domain walls, right? So that's x inverse. And let's say I'm at low temperature, then that x inverse goes like this, right? This is how it goes like, everybody agrees? And this is nothing. This is exactly how the correlation length of the 1D Ising model also behaves with temperature, right? Because this is exactly what's providing the correlation length to the system, right? So if you plot the correlation length of the Ising model, 1D Ising model, as a function of temperature, then of course at high temperature it's some very small length, maybe 1 lattice spacing, 2 lattice spacing, something like that. But then as you go towards low temperature, it diverges like that. It's always finite at any finite t. That's why there is no phase transition. But it diverges exponentially fast as you go towards t equal to 0. And that's the way it diverges, right? Of course, this is not an exact calculation. This is an approximate calculation, right? And for the 1D Ising model, you already know how to calculate the correlation function using transfer matrices, and that will give you the exact behavior of this with prefactors, etc., etc. But this is qualitatively correct. This is exactly how things behave. Okay, so I just wanted to point this out to you, because from what we discussed yesterday, this comes out very easily. Okay, so I just did not realize it yesterday. Okay. No. See, no. See, when temperature is small, yeah. So this is fine, right? X inverse, right? I'm taking x inverse because x is the density. X is the density, right? And then I say I want a length scale, so I've written x inverse. This is the This is like the average spacing between domain wall, average distance between domain walls.
Or the average size of the domain.
Or, exactly, or average size of a domain wall.
Domain.
Of a domain, exactly. So let's call it average size of a domain. Yeah, that's the way to say it, average size of a domain. Correct? Because of course, if this number is very small, that literally means you have domains like this, right? Very close by, right? The spins are oscillating very fast, right? Whereas if this number is very large, then of course you have some big fat things like this maybe, right? And it goes on. Something like this, right? Something like this. Okay, good. So this is one of the things I wanted to point out. Now there were a couple of other things as well. So let me just try to see. This was fine. Then in d equal to 2. So this was one thing that we did, right? Then for the two-dimensionalizing model, we again realize that there, when we made domains, because the energy depended on the perimeter, and because the entropy of how many ways we can create those domains, that had a particular scaling. Because of that, we saw that at d equal to 2, in fact, there is a possibility of a finite temperature phase transition. And in fact, what we did after that was more than that. We did this low temperature to high temperature duality, and we could actually predict the exact TC for the 2D Ising model, right? And this was, of course, exactly the same as what one obtains from Onsager's solution, right? So yesterday, when I wrote the expressions, I stopped at a certain point, and then somebody asked me, can it be put in a, you asked me, can it be put in a more symmetric form? So I'll just state the thing there, right? So it just says like 2 or 3 more lines of algebra, but I'll just tell you the final thing and you can try the algebra, right? So basically one just has to use properties of these hyperbolic functions. So what we stopped at yesterday was some form like this, right? Remember we were doing the high temperature expansion and the low temperature expansion, right? And so we actually landed up in a relation like this, and the second relation that we obtained was this, right? These are the two things that we obtained. Now, if you massage these expressions a bit more, in fact, what you can show is that you should obtain the following. Sine hyperbolic n by 2 beta star, again sine hyperbolic 2 beta. Okay? And the other relation corresponding to this is the following. Sine hyperbolic 2 beta and sine hyperbolic 2 beta star equal to 1. So this is exactly this and this is exactly this. Okay? And this is, as you can see, completely symmetric in beta and beta star. Right? So in some sense the duality is completely evident here. Okay? The high temperature, low temperature duality. And then of course the critical point is the solution of this equation when, this we discussed even yesterday, the solution of this equation when beta and beta star are the same, let's call this beta critical, is this, right? Good. Okay. No, before Onsager. So Onsager's solution was in 1944, whereas this work was in 1941 by Kramers and Wannier. Yeah, this was like 3 years before Onsager's solution. And we actually did the proof of this using the expansion of the partition function at low temperature and at high temperature. Then one thing which I gave you as a homework exercise, please try to do it if you haven't done. I said that take the 1D Ising model. See, we did the low temperature and high temperature expansion of the 2D Ising model. Now I am saying that please take the 1D Ising model, do the low temperature expansion. You'll get some series. Then try to see what is the radius of convergence of that series. You should get that the radius of convergence of that series is 0. Okay? And then this is slightly harder. Try to see if you can get the radius of convergence of the high temperature expansion for the 1 de-icing model, and then you should get that it's actually convergent for all temperature. Okay, but that's slightly harder. The low temperature part is easier to see. Okay, good. Then actually I realized that there is a nice work by Dom. Unfortunately, I don't know the exact reference, but the work was done sometime in the 1970s. 1970s. Okay, so basically what Dom did was he analyzed in lots of 2D models, he analyzed these low temperature and high temperature expansions and got their radius of convergence, and he could establish the presence of phase transitions just by using this trick. So, but unfortunately I don't know the exact reference right now, but I can.
I seem to remember the place where I have read it. It's an old book in KFL library. Old journal.
But I
forgot the name.
I know that the work was done by Dom. Yeah.
Dom article.
Right. And it's very interesting because, I mean, the methods he used, you can apply them far more generally. That's what I'm trying to say. Right. So it's, but maybe if you can dig out the article, we can circulate it later.
Very long article by Dom.
But one general point
Yeah.
about radius of convergence,
Yeah.
let's say high temperature expansion.
Yeah.
Of course, there will be a radius of convergence.
Yes.
But that radius of convergence sometimes will be smaller than
Correct.
DC because there's a singularity in the complex plane.
Right. So, thanks Mustansif for that comment. So, the sharper statement that I want to make is, if you can establish, starting from high temperature and from low temperature, that the radius of convergence is finite for both the series, then you necessarily know that there is a phase transition. That's a sharp statement. Why? Because you then know that whatever is the phase at high temperature is surviving through for a certain range of temperature at least, when you make the temperature finite this way, and the same for low temperature, right? And then of course, in many a times it's easy to establish that the nature of the low temperature phase is qualitatively different from the high temperature phase, because that's an easier thing to establish many of the times, and then you necessarily know that there is some phase transition in between, right? Okay.
The point I was trying to make is that you could have a smaller radius of convergence because of singularities.
In the complex plane, right.
I don't know how that would connect here, but you meant on the real axis.
I meant on the real axis, when I tune the temperature.
Okay, temperature.
Yes, because when I test the radius of convergence, what I want to test is in 1 by beta or in beta. Right. Okay, so that was another thing which I wanted to point out. And now today, because it's the last day, I'll just do simple things, and therefore I'll do mean field theory. But mean field theory is a very useful thing. Okay, so see, I mean, of course, when you get a general model, you don't try to do the most complicated thing first, right? You always, in anything, try to approach the problem as simply as possible to get the essential features of the problem. That's the goal of most of the physics we do, right? So I'll go in that vein. Okay, so good. So let's do the mean field theory of the Ising model. Okay, so that's my aim today, and then I'll discuss some aspects of what I get. Okay, so I'll discuss that. So let's stick to the mean field theory. But before that, are there any questions about anything? Okay, if not, then I continue. So I'll do a particular way of, I mean, there are many ways of doing mean field theory. I'll stick to a particular way because I believe that's the simplest way which leads you to the answer. So, yeah. So, when we will do the mean field theory, you will soon realize that we will be ignoring terms which are like second order in fluctuation. You will soon see what it means. Then you can ask, okay, if I have to think sort of in a really rigorous manner, is there a particular limit in which whatever mean field theory, which is an approximation that I am doing, is there a limit in which mean field theory becomes exact? The answer is yes. So we have been studying the d equal to 1 Ising model on some one-dimensional lattice. We can study the two-dimensional Ising model on the square lattice. We can study the three-dimensional Ising model if you wish on a cubic lattice. But now try to think even more than that. Let's think of a hypercubic lattice in 4 dimensions, 5 dimensions, 6 dimensions, infinite dimensions, right? So then d equal to 1 is something we have already studied. D equal to 2 we have studied using that high temperature, low temperature duality. And now we'll jump straight to d tending to infinity, because you can show, if you do some calculations, then you can show that whatever analysis I'm going to do right now is going to be exact when d is infinite, right? Infinite dimensional hypercubic lattice. You might say, oh, what does it at all tell me about the physics? What it would tell you about the physics is that there is a phase transition. So just by doing this very simple analysis, you will have gained some insight about this d equal to problem, d equal to 2 problem. But it doesn't stop here, okay? So let me go on and I'll point out why it doesn't stop here, okay? Good. But if you want a problem where mean field theory is exact, right? By exact, I really mean exact, then this is the place, okay? Good. Right, so now let's do the problem. So again we go to our favorite Hamiltonian, the Ising model. Let's also put a magnetic field. Okay, so now see, if the Ising model just had this term, the magnetic field term, then it's very easy to solve it, right? Because the partition function is just the product of, so the partition function z is just the product of z times n, where the small z is just the partition function of the single body problem, right? That we know how to solve. Good. So now we are trying to cast this problem in an effective one body problem. That's the aim of trying to do mean field theory, okay? So that we approach a solvable limit, but the parameter that enters this one body problem we'll then determine self-consistently, okay? So it's not that we are ignoring everything about the physics. We are in fact casting it in an effective one body problem, and then we'll determine whatever parameters are there in a self-consistent way, okay? That's the idea. So let's see what to do. So let me write it like this. You can imagine that this m, this symbol m that I have used, you can imagine that this is like an expectation value for the spin, right? So we know that for an Ising model problem, this can be non-zero if there is spontaneous symmetry breaking, even when the magnetic field is 0, right? Good. So we do that. So this is like the average then, and this is like the fluctuation about the average, right? Just by the way I've written this, but this is an exact statement. So similarly, we can do it like this here. So far there is no approximation. Now let's expand this term. So of course there will be a piece like this, then there will be 2 pieces like that, and then there will be another piece like this. So this term is linear in the fluctuation, right? And this term is the quadratic term in the fluctuation, and then we somehow make the approximation that the fluctuations are small, and we choose to ignore it. So we choose to ignore it. See, that's why in some sense this can become exact for infinite dimension, because in an infinite dimension, suppose you are looking at a spin, then, okay, so suppose, okay, let's see. So suppose you are in a 3-dimensional lattice. This spin feels the effect of this spin, this spin, this spin, this spin, this spin, and this spin. So it's like the sum of 6 variables acting on it, right? But if you go to infinite dimensions, of course, the number of variables acting on this spin is becoming incredibly large, and then you can think of it as a effective medium, if you wish, and that effective medium has basically no fluctuations, right? So in the infinite dimension, this thing becomes exact. There's a better way to show that, but here I'm just crossing out this term. Okay, good. So now, if I cross out this term, it's not that I have thrown out all the information. I mean, I still need to determine what is this effective medium M around this spin, right? And because that's here, right? So I need some way of figuring it out. But the nice thing is now this becomes again a solvable problem. So let's just go ahead and solve it, right? It's very easy to solve it. So then I get a minus m square, because here there is m square, there is a minus m square from here, there's a minus m square from here. So therefore, the total is minus m square plus an m Si plus Sj, right? This is the Hamiltonian. And of course, there's the magnetic part, right? So then what is your mean field Hamiltonian, if you wish? Mean field theory Hamiltonian, or let me just write mean field Hamiltonian. So there is this minus m square. Now, normally you might have said, oh, this is a constant, just ignore it. But now it's not a constant, this is a parameter which I need to self-consistently determine, right? So I cannot ignore this term, right? So this thing, because I'm summing over all the bonds, would come with a prefactor which is j times number of bonds, right? Good. Okay. So correct, because there's a minus, right? And then the rest of it just comes like this. Like this. So this is the mean field Hamiltonian. And the nice thing about this is, as I said, this is completely solvable. This is like a bunch of free spins again. So let's just go ahead and solve it, right? So then we can just calculate the partition function. No. See, as I said, this is m square. There is a minus m square, there's a minus m square. One minus cancels this plus, and there's one minus surviving. Right? So we just solve the partition function now. That is also, so there'll be a piece due to this guy. And then there's a piece due to this guy, right? But this guy, we can easily write, right? So that's just to the power n, right? Because it's just a bunch of non-interacting spins now, okay? Now, now you can of course do it. This would give you some cos hyperbolic of this object, right? But for notational convenience, let me just define the following. So I'll just define some dimensionless quantities. So this is the free energy per site, but I am also normalizing it by this energy factor J, right, which is this J, and this Z is the coordination number of the lattice, okay? So what is Z? Z is just the number of nearest neighbors to a point. So for a square lattice, Z is 4. For a one-dimensional lattice, Z is 2, so on and so forth, right? So this Z is just the coordination number. And of course, it comes naturally here because we are just summing over nearest neighbors here, right? So that's why. Okay. Then there is a dimensionless temperature which I define, which is again normalized by J, but I add this Z again to take into account that it's talking to Z things. And then there is this dimensionless magnetic field, which is again exactly in the same vein like this. Okay, good. And now we can just write the free energy from here, right? So as I said, this would give you some 2 times cos hyperbolic raised to the power n. But of course, free energy, for free energy, I need to take the log of this, so that'll just simplify. So we'll just write it here and analyze that mean field theory free energy. Oh, I see. Oh, okay. So let me write that on top. Wait. So let's write it here. So it's by Domb, right?
The book is this one. So this is collection of all his work.
Oh, I see. I see.
This is the article, but says 1960. Are you sure?
No. It's not 1960. It's later than that. It's
I
1970s.
remember having read it here, but
The long article is in the 60s.
that's in
But then maybe this is a later
this is
work.
another
But maybe I can mention the book if anybody wants it for the college library or something. So, DOMS. So the name of the book is The Critical Point.
quite written as an accessible.
Okay. So here is a suggestion for a good book for your college libraries or for your own personal libraries. Right? So, okay. So I'll leave it here and I'll erase the rest and continue with that analysis. So, okay, so let me now just write the free energy per site, but in these dimensionless variables, okay, just for convenience. So, of course, the free energy is a function of course, it's a function of temperature, it's a function of magnetic field. But here, because of the way we are casting the problem, it's also a function of this parameter m, which we need to determine, right? So, then you get the following times log of 2 cosh hyperbolic m plus h phi. So, very nice compact form. Okay, and then we need to determine this m, right? We don't know m right now, we need to determine it. So, how do you think we'll do it? This is the free energy, so we'll just minimize it again, right? Good. Because of course, as we know, at finite temperature, we should not minimize energy, we should minimize free energy, and that gives us the right stat-mech description, okay? So, once we minimize it, you get a very familiar, familiar equation. Like this, right? So, this equation was to be expected even from here, right? Even from this point. I mean, but I'll show you soon that there is an advantage to writing this free energy, because we can interpret it in a very nice manner, and we'll soon see that. Okay, so why can I get this from here? Because as I said, the spin, it's like this, right? So there's a spin, and let's draw the other spins with white. There are all kinds of other spins, some of them may be down, some of them may be up, right? Because of course it's some fluctuating environment. And so we are looking at this spin, and we are looking at its environment, and somehow we are replacing the effect of the environment by this spin feeling some effective expectation value around it, right? So then that's exactly what's causing this field, right? So there is a J here because of this, J is a M here because that's this effective strength of the polarization, right? Because this is the definition of M. And there's the Z here because this is the structure of the interaction, so the nearest neighbors interact to it, then that's why there is this whole piece, right? And now this is a free spin, and this is the magnetic field which it feels, therefore the right hand side has to look like this, has to look like the tan hyperbolic beta times that magnetic, effective magnetic field, and that's exactly what it is in those units. Good. So now this you must know, but I'll just refresh your memory again. So this guy, of course, okay, now let's actually directly go to the more interesting case. Let's put h equal to 0. So we put h equal to 0, so I erase the h here, okay? Good. So it's a slightly simpler looking equation. This guy has one obvious solution, which I guess all of you immediately see. What is the obvious solution? Yeah, correct. So this is the obvious solution, m equal to 0, which is what we would physically expect at 0 magnetic field, right? And in terms of whatever we have studied yesterday and also heard from the previous lectures, this is the unbroken symmetry state, right, where this Z2 symmetry is not broken, unbroken symmetry state, or in more conventional language, this is the paramagnetic state or the high temperature state of the Ising model. Okay, I need some more chalk. Good. But now the question is that the only solution to this nonlinear equation? And the answer is no, right? And then what we do is we can just sort of graphically figure it out, right? So the point is that what we just do is we draw this curve, and that's just a straight line here, right? Because it's a line with 45-degree slope, and then we look at this tan hyperbolic function. Now, tan hyperbolic function near the origin is just a linear function again. Therefore, what it automatically, but of course the tan hyperbolic function then has to converge to 1 and minus 1. So what it means is if I choose a theta such that my slope at the origin is greater than 1, right? So let's say this is the origin and my slope is greater than 1, and that can just be done by choosing theta appropriately, right? Then I would get something like this. Hopefully it's symmetric. Yeah, it's actually symmetric. So then there are three solutions. And the magic theta, where it happens is, of course, you can just guess the answer because there's a very simple structure. So what is the answer? What? What is the theta below which there is 3 solutions and above which there is only 1 solution? What is that theta? Correct. Because of course if you put theta less than 1, then the slope is higher than 1, right? Good. So theta critical is 1, which implies that in mean field theory, it seems that there might be a transition. Well, we haven't shown it yet. So let's just still write this as theta critical, and theta critical is z times j, right? Good. It's z times j. But now we have got 3 solutions. Now can somebody tell me how do I know which is the correct solution? I mean, there are 3 solutions here. Which one is the correct solution? In the case where there is only 1 solution, it's easy. That's the correct solution. But here there are 3 solutions. What do I do? Yeah, you can do that. That is correct. But what am I looking for? Right. So one way to do it is you can calculate the free energy at this point. You can calculate it at this point and at this point. Whichever is lower, that's your thermodynamic state, right? So we will actually do it slightly better than that. So let's look at this expression. Okay, when we do this graphical solution, it can be shown that when theta is being decreased towards 1, so when theta is 1, there is only one intersection of this curve. I'm really bad at drawing, but I'll still try to draw. Something like that, right? Because the slope here is less than this guy, right? And then this guy moves like this, and then it does this, right? So this intersection, when it first happens, it's arbitrarily close to the origin, and then of course as the slope changes, it moves further and further apart. And this mean field theory analysis shows that the order parameter stays 0 and then continuously increases after you cross below this temperature, right? So okay, good. So then if I am slightly below this 1, I know that these intersections are very close to the origin, right? So there is only the origin and these intersections which are very close to the origin. So m is small. That's the key point. So because m is small, I can do a Taylor expansion of this free energy, right? So that's exactly what I'll do, because you know, then if I do a Taylor expansion, this will start looking like a much simpler object. So let's just do that. Let's do the Taylor expansion, right? Good. And of course now I don't need to write h because I put h equal to 0, right? So when I do the Taylor expansion, this is what I'll get. So actually let me just write down the result directly. You can verify that this is the correct result if you do a small m expansion. So minus theta times log 2 plus half this is what you get. This is what you get. Okay, so now let's look at this function. So this is a function which is a function of m. Once I tell you a temperature, then the only variable it depends on, this free energy, is m. So if I just draw this free energy as a function of m, it should tell me where its minima are, right? So let's do this. So notice one interesting thing. So of course I can sort of ignore this because this is a constant piece. It does not depend on m. So the interesting piece is this guy and this guy, right? So look at this term inside the bracket. So let's say theta is the temperature, theta is greater than 1. Then what is the sign of this term? Right? That should be clear. When the temperature is greater than 1, right? Effective temperature, this normalized temperature. Whereas when theta is less than 1, the sign changes, right? Good. So let's just draw this. So I'm drawing f of m versus m. So let's consider the first case when theta is greater than 1. Then it should be easy. What should I draw for the free energy? No. Careful, not this. So I'm ignoring this, by the way, just for simplicity. So I have this. This is positive. This is also positive. So what should I draw? Yeah. Right. So it's a symmetric curve, and she was making the right motion. So right. So this is how the curve looks like. Right? Okay. Good. So this is for theta greater than theta c, or 1, right? Which is 1 in this case. Now let's put theta to be less than 1, slightly less than 1, right? Then what is going to happen? Then how does this curve look like? So what happens near m equal to 0? Near m equal to 0, okay, so let's first look. Near m equal to 0, I can just think about this because m4 would be much smaller than m square. No. Well, okay, almost right. Okay. Oh, I don't know which way you were starting from. Right. So that's correct. So near m equal to 0, m4 is of course much smaller than m square, right? Because m is a very small number. So then this is like an inverted parabola, right? Because this coefficient is negative. So the thing has to start like this, right? But as m becomes larger and larger, m4 will start dominating, and then you will actually get something like this, right? So this is when theta is less than theta c, right? And now it should be clear to you what's going to happen. So when theta is above theta c, the system will choose this free energy minimum, right? Because that's the unique minimum. Whereas if theta is below theta c, then of course this is not a minimum, this is a maximum. That's why df by dm equal to 0 is also solved by this point, because this is a maximum, right? But we are looking for the free energy minimum, and there are two equivalent minima, right? So either the system can go here or it can go here, right? So here is a situation where there is spontaneous symmetry breaking, right? And we can even estimate the temperature at which it happens, right? So this is, and of course, as I said, if you decrease m, then what is going to happen is that these curves sort of, not like that, yeah, these curves sort of move closer and closer, right? So if you wish, if you plot m as a function of theta, and theta equal to 1 is a special point, above it, it's 0, whereas below it, it increases smoothly, right? So we have shown from mean field theory that there is a continuous phase transition at theta equal to 1 for the Ising model, right? Yeah? Oh yeah, of course. Both of them, of course. Thank you. That's correct. That's absolutely correct. Oh, that reminds me of a question which was asked. I think Mustansir suggested that exercise to you. Right. Remember? Okay. You shouldn't have asked this question, but anyway. Yeah. So this was the M versus T graph for even the 2D Ising model, something like that, right? then the question was, what happens if I think of the same physics in the HT plane? Right? So what do you think happens? I mean, the only special point here is TC, right? So now try to answer what happens, what do you think will happen in the HT plane? So the question is clear, right? I have the same ferromagnet. Now let's go step by step. I can try to help you, then you can answer me. Let's say my temperature is below TC. Let's say it's below TC, right? So let's say the temperature is here, right? Then let's say I have a finite H, right? Then of course if I have a finite H, I have a finite magnetization. That's not a surprise. But if I'm below TC and then I'm at even a very small H, do you think the magnetization would be small or large? Correct. We saw that, right? That was in fact the definition of spontaneous broken symmetry. And then if you go on the other side, what is going to happen? Negative, but again large, right? So there is a jump in the order parameter. So what do you think is going to happen here at this point? Is there a transition? Is there anything? First order transition, right? And so is there a first order transition all through? So what should I do? Till TC, right? And then there is a critical endpoint here, which is a continuous phase transition. And then beyond it, of course, there is a magnetization at a finite H. But if the H is very small, the magnetization is also going to be very small. And when H is 0, the magnetization is going to be 0. That's exactly what we learned yesterday. That was the definition, right, of spontaneous symmetry breaking. So here, when I take the limit from here and from here, I should get the same value, and the only value that I'll get is 0. Whereas here, there'll be a macroscopic jump, right? So this is the phase diagram here. Now, okay, coming back to your question, thank you for this observation. Of course, there's a negative branch also. So if you take a system, the system sort of spontaneously chooses either the up branch or the down branch, right? That's a random thing which maybe some external perturbation decides or some stray field decides or something like that, right? Good. So far, so good? Okay. So now, let me tell you why we are spending so much time in studying this critical point, right? So, we are spending so much time in studying this critical point for the Ising model where we could exactly solve it, and for all these other models, because the critical point has an amazing property called universality. Okay? So, what does that mean? So, we talked about the Ising model, right? Now, let me describe another model to you, and I can also ask you some simple questions at 0 temperature about what's the ground state, and it'll sort of wake you up, right? And well, you look more or less awake, but it'll wake you up even more, okay? So, and then we'll discuss universality. Okay, so mean field theory is hopefully clear. I'll explain this further. This is very interesting and important. In fact, yeah, I mean, of course, without going into too much depth, it's sort of also easy to introduce this whole Landau-Ginzburg sort of free energy from here, right? But let's keep this here and we'll come back to this soon. But one thing which you should appreciate is, look at this. This critical temperature is what? Z times J, right? So what is this predicting? It's predicting that even in one dimension there is a phase transition, right? Because in one dimension I would say that Z is equal to 2. So then there should be a phase transition at 2 times J, right? But of course we have analytically shown that in one dimension there is no phase transition. But that is okay, because mean field theory is an approximation which is supposed to work exactly here, right? There is no sort of sense in saying that mean field theory will even work here, okay? Okay, so the point is that, the first point is that mean field theory is good at telling you qualitatively the phase diagram, right? So if you are clever and you can guess what sort of broken symmetry you expect, you should try to do a mean field calculation and see whether that's actually true, and then mean field theory can help you give the phase diagram, right? It's correctly telling you that if the phase transition happens, there's a ferromagnetic phase and there's a paramagnetic phase. So that's qualitatively correct. Where the transition happens and other details, they of course require more elaborate calculations, right? The second thing is, in mean field theory, we have thrown out certain fluctuations, right? So these fluctuations, which were very small for d tending to infinity, as you keep lowering your dimension, these fluctuations become more and more important. And in fact, in one dimension, they are so important that they make even the basic result of mean field theory wrong, which is that there is a phase transition, right? But it's not so bad, because from d equal to 2 onwards, we do have a phase transition, right? Okay. And therefore, typically the mean field theory critical temperature estimate is always an overestimate, because you have ignored certain fluctuations. Typically, your actual TC typically is going to be smaller than the mean field answer. Okay, so that's something to remember. Good. So now let me erase this and go to a slight generalization of the Ising model, and let's discuss this for a minute, and then you can, then we can discuss this thing of universality as well. Okay. Now, so let's again take the square lattice, and then on each side there is an Ising variable, right? On each side there is an Ising variable, which can be plus or minus 1 as before. Okay, good. Now, what is our normalizing model? The normalizing model is that this spin interacts with its nearest neighbors, right? So it interacts with this guy, this guy, this guy, this guy, right? So let me just write that. So let me slightly change my notation and write a J1 here. Okay. So these interactions, the nearest neighbor interactions, I denote by the symbol J1. So ferromagnetic interactions. Okay. Now let me say that the interactions do not stop at nearest neighbor. There are next nearest neighbor interactions also, right? So what are the next nearest neighbor of this point? So the next nearest neighbors of this point are, what are they? Correct. So there are only 4, right? 4. These guys, this, right? So this guy also talks to this guy. But now the interaction is a antiferromagnetic interaction, okay? So what it means is if this spin is up, then this energy wants that spin to be down, okay? So it's an antiferromagnetic interaction. So let's write it with this color. Oh, I should change my notation now. Okay. This symbol means next nearest neighbor interactions. Oh, sorry, K. So this is on the square lattice. So this is a J1, J2 model on the square lattice. J1, J2 Ising model on the square lattice. So now let's try to draw the phase diagram of this model. Okay. So let's see. So then, of course, you should think of 2 ratios here. This, and of course there's a temperature axis. This. Now this is not the Ising model, right? Now we cannot solve it exactly. It's not possible to solve it exactly. But of course still we can guess a lot of physics, right? I mean, you don't have to always solve a problem exactly to understand its physics, right? That's what I'm trying to drive at. Okay, so this is 0 temperature. Okay. Now let's stick to 0 temperature. Can people tell me what is sort of the ground state you expect at 0 temperature? Let's start with easy limits. Let's start with easy limits. Let's say J2 is very small. Then what is the ground state? Huh? Yeah, all up or all down. Right? So it's ferromagnetic, right? In one limit. Okay, good. So let's just draw that thing as a cartoon here. So I denote up spins by maybe, let's say, filled things, right? Because actually this is faster to draw for me. So this is, of course, ferro, right? Something like this. Good. This is enough. Okay. Okay. So ferro here at the ground state. Good. And of course, this state breaks. What symmetry? This state breaks. So please notice this Hamiltonian also has a Z2 symmetry, right? Is that clear? Why? Because if I do this action, the Hamiltonian again stays the same. So again it has the Z2 symmetry. And this phase breaks Z2 symmetry, right? Okay, now what happens if I keep increasing the J2? Do you think something else should happen? Antiferro, think. Okay, let's take a very high J2. What do you think should happen? What should the ground state look like? Very high J2. There is another way of then thinking about this problem in a very straightforward manner. Think of very high J2. Is there any simplification? You can of course ignore J1. Then is there some simplification? Huh? What is bipartite? Okay, maybe you're saying the right thing, but okay, you have to say it a bit clearer for me to understand. Maybe you're saying the right thing. So, okay, so the point is, I can ignore nearest neighbor interactions, right? So, good. So then, I don't know if that's obvious to you, but think about it. Then this problem just reduces to two interpenetrating square lattices, right? Which are not talking to each other. Okay, I mean, well, there isn't. Okay, my drawing, okay, let's try. This is one sort of a square lattice, right? See, when I'm drawing this square lattice, I'm only using next nearest neighbors. Please remember that. I'm not using nearest neighbors because when J1 is 0, I can forget about the nearest neighbors, right? So that's why I'm drawing a square lattice like this. So that's one square lattice. And then there should be another square lattice, right? So let's use some other color. Yeah. So of course, there's this square lattice, right? Sorry, this is a bit of a clumsy figure, but hopefully you see what I'm doing, right? There are two square lattices which are not talking to each other, right? And each square lattice is just a simple antiferromagnet, right? On this, right? So on one square lattice, the antiferromagnet can have two states, right? Because it can have one possible staggered state and another possible staggered state. On the other square lattice also it can have two possible states. So how many degenerate states would you have? 4, correct. And I'll just draw the ground states. You can easily verify that's the correct answer, okay? By minimizing energy. So the 4 ground states are these. So I'll just draw one, then you tell me what are the other ones. Sorry, this drawing is not very accurate because there seems to be more spins here, but okay. I mean, you have to excuse my drawing abilities. Okay, this is one kind of a ground state. What are the other ones? There should be 3 other ones. Do you see some pattern here in this ground state? Does anybody see any pattern? Correct. Correct. Absolutely. Just to guide your hand, think like this. One stripe of one color, another stripe of the opposite color. One stripe of one color, another stripe of the opposite color. And exactly, so let's put 2 arrows, 1 arrow, 2 arrow. And exactly of the, yeah. So then let's say I only want vertical stripes. Is there any other natural state? I mean, this is one state. What is the other state I can draw? Let's say this is my origin, right? Let's say this is my origin. And let's say this is my, I mean, I'm drawing the thing like this. What is the other state I can draw? Correct. Right, this is the other state. First I can do this, right? And then I do this. Everybody agrees? Good, so this is another state. Okay. Good. Then, is there anything else which is possible? Correct, absolutely. So these are vertical stripes, I can do it with horizontal stripes, and then there are again two options. So let me just quickly draw them. And of course the partner of this guy. So now you see this state is also breaking a symmetry, but this is not Z2. This is actually a Z4 symmetry broken state. So this is Z2, but this is a Z4 symmetry broken state, right? Oh, I don't know if the mic is on, but probably you can hear me. Oh, okay, it's on. Yeah, somehow, okay. Right. So this is a Z4 symmetry broken, right? Because you have to do this symmetry operation 4 times and then you come back, right? Good. And clearly this is not a ferromagnetic state, right? This is not a ferromagnetic state. Good. So this is in fact what is called a striped state for obvious reasons, because there are these stripes here, right? Good. So this is ferro here at 0 temperature. This is striped here. Now, what do you think will happen? This is striped, this is ferro. They are different from each other. Only one thing can happen. Right, phase transition. So there is in fact a first order phase transition here from a ferromagnetic phase to a striped phase. And this again you can verify for yourself. See, okay, I'm not going to do this in real time for you. You can verify this yourself by the following trick. Write this Hamiltonian as, so just look at this Hamiltonian at the level of a single square and then try to minimize energy and then try to build up the entire spin configuration from that. You would be able to derive whatever I'm going to say, okay? So, right. So then, so this J2 by J1, let's just put a shorthand, let's call it G. So then when G is 0.5 or half, then there is actually a phase transition from ferro to stripe, okay? So in fact, what happens here is interesting. So you see here what happens, so you can ask what's the state here at this point. See here what happens is, and I was just inspired by this example from what Mustan sir told me at the break. So, but this is sub-extensive entropy though, okay. So, so what happens here is that at this state there's a huge degeneracy of possible ground states. So how do you choose those possible ground states? See here in the ordered side, if this is, let's call it white and black, right? So if this stripe is white and this is black, then this is automatically white and black. So I fix one stripe, everything else is fixed, right? If I fix a vertical stripe, then everything is fixed. If I fix a horizontal stripe, everything is fixed. Here, if I fix one stripe, the other stripes can just fluctuate completely independently, okay? So you can make this stripe black or white, it's your wish. You can make this stripe black or white, it's your wish, so on and so forth. But only at this special point, right? So then effectively there is, so if there's an L cross L lattice, effectively it's like a 2 to the L times 2, because vertical times horizontal. So effectively there are these many ground states if you have a L cross L square lattice, okay? Because each thing has a degeneracy of 2 and you can do it independently, so 2 to the L, and you can do it either with vertical orientations or with horizontal orientations, and that's the 2. So 2 times 2 to the L. So a huge number of ground states, right? Okay, good. So that's the phase diagram here. Good. So now, this model I cannot solve, right? But at least I know from physical grounds that if I raise my temperature, somewhere it should become a paramagnet, right? The magnetic order should be lost. Now then, one very reasonable thing is, maybe something like this happens. So it goes from ferro to para. Let's not discuss this side right now. Let's say that there's a wall of ignorance here. I'll just give you the phase diagram. I won't keep you too ignorant, but I mean, this requires, of course, more analysis and thought. But let's just talk about this guy. So let's say this ferromagnet, as I keep increasing the temperature here, goes into a paramagnet, right? But see, this model I have no way of solving exactly. I have no way of exactly solving it I can only solve this point, right? Exactly, due to Onsager. This is the Ising limit. And I can only solve the extreme other point, because that's also the Ising limit, right? Nowhere in between can I solve this model. But then I am saying that this phase transition has the same long range physics, has the same long distance physics as the phase transition I have obtained in the 2D Ising model, right? Even though this is a completely different model. And that I am saying simply because this model breaks the same symmetry. So let me sharpen the statement and I'll just mention a few consequences of that. I mean, to show that rigorously takes a lot of work, but let me just at least give you the statement because this is very important. So, universality. Okay. So before I go on to universality, let me just lift this veil of ignorance and tell you what happens on this other side. So on this other side, something very peculiar happens. So there is a very weak first, okay, so this dashed line means weak first order. So this is striped and then it becomes para, okay. So this is very weakly first order all through. Then there is a tri-critical point at some G star which is roughly 0.68, some number. This number you can get only after a lot of hard work and Monte Carlo algorithms. There's no other way of getting this number. And then there is a phase transition. Then you can ask, what is the nature? What is the universality of this phase transition? I mean, that's again a hard question. In the extreme end, it's again in the Ising universality class, in the extreme end. I mean, I'm drawing an endpoint here, but of course there's no endpoint here. It's really going to infinity. That's because there are these two interpenetrating lattices with staggered antiferromagnetism, and we just argued yesterday that that should be in the same universality as the ferromagnetic Ising model. Whereas everywhere else along this line, the universality of the transition keeps changing, okay? So this point, so I won't say too much about this, I'll just mention some names. For some of you it might ring a bell, but even if it doesn't, these are very well-known models, you can always go and look at them later. So at this point, the universality is in the Q equal to 4 Potts universality class. Okay, that's some phase transition which is very different from what we have been studying. It's again a phase transition from some one discrete symmetry to something which does not break that symmetry, but this is it. And then it ultimately flows to the Ising one. So the exponent, okay, I haven't defined the exponents, I'll do it today. But the universality of the phase transition keeps changing along this line, okay? So, right, we'll see what it means. So I'll tell you a definition of universality now, and in fact you will then soon object and tell me, oh, but this guy does not satisfy universality. But in fact it does, and it's called weak universality. There's again a precise notion of that. But let's not go into that for this set of lectures. Okay. Okay. Good. So what is universality? Okay. For that, okay, let me first give the statement, then we'll discuss it. So basically what I'm trying to say is the following. So suppose you have some continuous suppose you have some continuous phase transition, right? So continuous phase transition means there is some physical system in which you have identified some order parameter, and let's say your tuning temperature, and the order parameter is smoothly going to 0 and then staying 0. That's the meaning of continuous phase transition. That's what we defined yesterday, right? Good. So now suppose you have a system like this where there's a continuous phase transition. So the order parameter is characterizing some underlying symmetry of the Hamiltonian which you are breaking, right? So for the Ising model it's Z2, and for some other complicated problem it might be something more complicated, right? Z2 is the simpler example, right? So then suppose you have any physical system which has such a kind of a phase transition, then you're trying to understand the nature of the physics here, and then this thing kicks in. So the things you have to look at is the nature or the symmetry of the order parameter, right? Of the order parameter. So that's the first thing. Then the second thing you required is the dimensionality of the system, whether my system is 1D, 2D, 3D, 4D, infinite D, okay? And the third thing that you need is short range interactions. Okay? So the point is, if you are considering two completely different models where these 3 points are identical, then you can claim that the nature of the phase transition is identical between the two systems. So this is a very powerful statement, right? And this is what is called as universality. You might take this Ising magnet or this completely different J1, J2 magnet, and then I can still claim that this phase transition is exactly the same phase transition as is happening here, right? Why am I claiming that? This system is in 2 dimensions. This system is also in 2 dimensions. This system has short range interactions. The Ising system, which we discussed yesterday, also has short range interactions. And the symmetry that we are breaking spontaneously is a Z2 symmetry here, and it was a Z2 symmetry even there. That's it. So the 3 conditions are satisfied. So without doing anything, I can tell you that if there is a continuous phase transition, so the statement is very precise. If there is a continuous phase transition, then it's in the same universality class. It might happen that there can be some first order phase transition here. And then of course this doesn't work. So I'm saying if there is a continuous phase transition, if you realize that this phase transition is continuous, then it's in the same universality class as the 2D Ising model you have already studied. Okay, so that's the statement. Good. So for example, you might have already discussed, have they discussed this equivalence between lattice gases and?
No.
Oh, I see. So, okay. So, you see, okay. So, I think PK was mentioning that the Ising variable can be thought of to be as many things, right? Anything which is 2-state, right? So, you can imagine that the Ising variable defines something which is empty versus filled, right? So then again, a very nice place to look at various different kinds of Ising models which are effectively described by the same short range Hamiltonian is Kersen-Huang. Okay? So there you will see that there is an entire section on lattice gases, and lattice gases are a minimal model to describe, if you wish, the phase transition between a liquid and a gas. Okay? And then you see the liquid gas phase diagram, if you remember, has a, of course it's normally first order, but it has a critical endpoint, right? It has a critical endpoint. Then by the statement of universality, the critical endpoint would be in the same universality class as the Ising model in 3 dimensions. And in fact, people have also seen that experimentally. So see the power of the statement, right? I mean, I don't have to do any calculations and I'm telling you all these statements. Of course, there is a very strong basis to all these statements, and the strong basis, the really mathematical foundation of this is provided by the renormalization group theory. Unfortunately, I won't talk of it here because I mean that's quite technical, but I mean the main idea is very easy to remember, right? This is the idea, okay? So right. So that's one thing I wanted to stress, which I didn't stress yesterday. Then the second thing is, when people test these ideas of universality and also in particular study phase transitions, I told you that there are all these fluctuations taking place, very strong fluctuations taking place near the phase transitions. Now there are certain quantities which are much more traditional to look at, and people define something called critical exponents looking at the behavior of those quantities. So I'll now give you a definition of just those things, and yeah, and you can also make the claim that if 2 models have the same universality, then those exponents are also identical. Okay, so that's another very powerful statement, right? Good. So let me just do it here. And for the mean field theory, we can even calculate those exponents, right? So because we have the full answer here. And for the 2D Ising model also, we know those exponents because we know the Onsager solution, okay? And for many other cases which are more complicated also, we know, for some cases we know those exponents with some other exact solutions. For many other cases, we know those exponents, maybe by using very nice Monte Carlo techniques and something called finite size scaling, or some other techniques, okay? But there are only very few problems where those exponents are really exactly known, but nonetheless, I mean, we have enough examples to believe that this statement is completely right, okay? We haven't found any exception to this thing. I mean, of course, I already wrote an exception there, weak universality, but that also can be understood within the scheme of renormalization group theory. Okay, it's not that it's something which is outside the framework that we believe is true. So let's just but are there any questions? I mean, okay.
So this short-range interaction is a very specific condition. So
It's not very specific. I mean,
if this is not valid, then you cannot talk about similar concepts.
well, I won't make such a strong statement. I mean, okay. If this is true, then certainly you can talk about universality, right? I'm not saying that for long-range models, there is no such concept. I mean, maybe there the validity is slightly more limited. But, I mean, this is that it's almost like a theorem if you wish. If this is true, then you can always say this. But even in long-range systems, there are some weaker notions, most likely, I think. But do you...
So you might mention that short-range interactions doesn't mean it's a finite range.
No. Yeah.
It could be exponentially decay.
That's correct.
Power law decay.
Yeah, it could be power law decay also with a sufficiently large exponent. Yeah,
In d dimensions, if it decays faster than 1 over r to the d, it's short.
exactly. So d plus alpha, where alpha is a positive number. Okay, so you see it's not very restrictive, right? Because most things in nature do go like this, or even if they go like power law, maybe ultimately there is a cutoff. See, even things where there are electrostatic interactions and all, typically there are always some screening effects which ultimately cut off the power law, right? So it's not a very bad approximation.
Interactions between molecules and liquids,
Yeah,
or anything that we know,
Yeah.
all obey this.
exactly, exactly.
Van der Waals, 1 over
Yeah.
r to the 6, 1 over
It obeys this, exactly. Right, so yeah, I mean, this is a fairly large class of systems, right? It's a very powerful statement. Of course, you're right. I mean, if I take a really long range thing which doesn't obey this, I don't know whether you can make such powerful statements, but even there, maybe there is some weaker conditions.
It's
Yeah,
very slow.
Yeah.
And it becomes mean fields.
that is also true. And if it's, yeah, that's true. If it's even slower, you might even have to worry whether the thermodynamic limit exists. So, right. Okay, okay. Anyway, but this is quite general. You can spend your entire life thinking about problems like this. And in nature, this is,
By the way.
what?
No, it may even be worth it.
Oh yeah, that's true. It's, yeah. Correct. Yeah. Yeah, this is quite a broad class of problem. Good. So, as I said, I mean, let me define certain quantities like this. Okay, so another thing about this universality, right? So, this I won't again discuss in any great detail, but you see, in Professor Banerjee's lectures and some other lectures as well, you were looking at all kinds of things like relevant directions and irrelevant directions. Oh, my fingers are going the wrong way. Irrelevant directions and relevant directions, right? So there is a beautiful correspondence here. So when I talk of these Ising type transitions, okay, so I won't discuss this in any detail, but I'll just mention it as a fact which will again be helpful to remember. And then if some people are interested, they can read it up on their own. But this fact is easy to state and remember. So any sort of phase transition has some relevant directions. I'll mention what it means, and some irrelevant directions. So what it means is, maybe there is a theory in which there are all sorts of couplings, right? Nearest neighbor coupling, next nearest neighbor coupling, next to next nearest neighbor coupling, so on and so forth. Then you can of course ask me, how on earth can I hope to get a universal theory of such a thing, right? Because one theory might have 20,000 couplings, for example, and I still can call it short range, because 20,000 is small compared to an infinite lattice size, right? Good. However, let's just stick to this Ising kind of example where there is a Z2 symmetry breaking. Here, you can always show that if there is an Ising-like phase transition, then there are only two relevant directions. There are only two relevant directions. One is a temperature-like direction or thermal direction. Okay, so I don't have a better word for it, maybe temperature-like or thermal. And one is a magnetic field-like direction. Okay, and then these are like your two knobs, and you have to fine tune those knobs, and when you fine tune those knobs, you reach the critical point. In our Ising model example, it's clear what these two knobs are. One is temperature, one is magnetic field. We have to tune both of them. This is a thing to appreciate. See, it may seem to you that, oh, why am I talking of magnetic field? Of course, I had to set magnetic field to 0. Only then was there a spontaneous symmetry breaking. And then my TC I had to set to TC, right? So these two knobs have to be set. In some more general example, you have to find the knobs. But once you found the knobs, these are the only two things you have to set. So what it means is, again, let's try to draw some flow diagrams. You have already experienced many flow diagrams. So there is some fixed point, some magic point you need to reach, right? And this is your critical point. So these two are your relevant directions. So what it means is, the flow is like this, right? So if you're not exactly sitting here or here, the flow will take you away from this critical point. And then there is something like a basin of attraction, in the sense that all other directions, they are irrelevant. If you're sufficiently close to the thing, they'll all sort of take you into the fixed point. Yeah. Oh, sorry. Oh, no. These are going in. Yeah. Oh, sorry. Maybe this is the confusion. Let me use different colors.
Two are going out.
The two relevant directions.
And,
everything else is, yeah, which is correct.
Okay.
Right. Because, yeah, there are only two.
Okay.
Yeah.
So all these other things are also coming into the fixed.
Exactly. That's what the point is. These are all irrelevant directions, right? So that's how you see two completely different models can share the same universal physics, right? Because you see, I mean, otherwise you have to worry about every microscopic detail of model number 1 versus model number 2. I'm saying, I'm sorry, I cannot give you a clearer representation of this right now, but essentially there are these two knobs or these two relevant directions which you have to fine tune. These are, if you wish, the things you have to fine tune in an experiment to get to a critical point. And then once you do that, you don't worry about anything else, right? So this is the general structure of how things happen. Okay, so, and then if you start even with a generalized Ising model which may have many interactions present, but still you would know that if it's having a continuous phase transition from a Z2 broken to a Z2 unbroken phase, then you can just use this formalism and say that it will have the same long distance physics as the 2D short nearest neighbor Ising model that we have solved. Okay, I think I'll introduce all these exponents and some other things in the next class in view of time. But since we have 1 or 2 minutes left, if anybody has any question, I can. Okay, then we can break for tea.
Yes.